Awesome. So yeah, just a slight correction there on the description. The latency wasn't zero point 0.5. That's my mistake. It was around 5 milliseconds. That's just something inherent with the circuit, which is still fairly low. And I'll move on to a brief description. Now, I think we heard descriptions from James earlier about lectin syndrome or LIS. And I wanted to talk a little bit about what type of what type of muscles it affects and how we can try to target certain types of movement. So James, if I'm not mistaken, he talked about specific opportunities to discuss and to communicate with these people who are afflicted by these conditions. Now, from my research, almost all individuals with LIS do have some sort of movement capabilities in the eye. So they can look up or down, some can look in both directions. And that was mainly an exploration of how certain types of cranial nerves aren't really affected by the motor degeneration that happens throughout the body with this. Now, I do want to talk about how this was applicable as well to ALS and nonverbal autism or certain conditions in which verbal communication is very hard or there's difficulty to kind of maintain control over muscles that aren't directly connected to the eye motor, to motor, uh, motor muscles in the eye. So there is an exception here. The research paper focused mainly on locked-in syndrome. However, there is applicability to ALS in certain earlier onset conditions because I know after a while, those muscles in the eye region do degenerate. So the focus was to try to find a way of providing cheap communication for these individuals in a way that wouldn't impair their independence in communication and reducing barriers of entry for people from low income backgrounds. Because now, throughout my life, I've lived in about 5 different countries, and 3 of them were in the global south. So one issue you hear a lot is that a lot of these people with disabilities do not have the proper opportunities to access accessibility technology or ways of facilitating communication or enabling them to communicate and be more independent. So, for example, in Brazil, there is a form of free healthcare. There is a free healthcare system. However, the wait times for certain accessibility tech is fairly long, or there are costly alternatives in case you don't want to be put on a years long list. If I'm not mistaken, one of the guests earlier from Norway mentioned issues with regulatory hurdles or difficulty accessing certain technology. So imagine that issue already in a Western country and just exacerbated even more in countries like Romania or Brazil, where you have the inherent issue with financing. Now, moving on to our motivations, I do want to briefly mention that my co-author wasn't able to join us today. Now, we're both in a time zone that is fairly early compared to the UK. So I was up at around 3 a.m. today getting ready for this.
Oh, thank you. Thank you
So
so much, Andre.
it's totally fine. It was honestly very exciting to hear all the presentations and help me really hone in some of the commentary. And I do feel like there's a lot of good ideas out there, and I want to kind of present our motivations. So commercial eye trackers, they usually rely on infrared and camera tracking. So that was something James, if I'm not mistaken, mentioned earlier, in that it is more efficient in the sense that you can capture more movement. However, it is costlier. And our main idea, parting from this research presentation, was to reduce a lot of the software complexity you'll see in commercial products because you have issues in countries that do not have a well-developed educational system, or at least a publicly accessible one with a lot of access to funds, in the sense that people don't really have the opportunities to learn how to code to the same extent you'd see in countries like Germany or the United States. So we wanted to kind of provide an opportunity that was very mechanical heavy, so mainly based on electronic components. Now, when we were doing research, we found commercial eye trackers that cost from 1K to $10,000. They require ongoing calibration, complex optics, and is something that you can see in the image on the left here. I put a little citation at the bottom. So this is a different company, Viewpoint Systems, if I'm not mistaken. There you go, Viewpoint Systems. So they have a very costly technology, and it's something that we wanted to avoid. So when we were doing our background research beforehand or literature review, a lot of it actually came from the software design and the technology itself. So we kind of try to drift away from that while avoiding certain interfaces that were too costly or had too little research into it, like EEGs. So yeah, EEGs, which measures brain signals, and they tend to be more accurate, but the issue is that it's very costly to actually maintain. And if you want to retain a certain type of like non-medical appearance, like you want to kind of reduce a lot of stuff cluttered on your head, that's a very difficult thing to do with an EEG. Meanwhile, EOGs are mainly meant to capture signals from the muscles around your eye. So an interesting thing about your eye is that it forms little dipoles. So when you look up, there's a more positive charge there. And when you look down, it kind of creates a more negative charge. So that's something you wanted to try to hone, because measuring this displacement in eye movement is very important to facilitate the sort of communication. Now, when we started building, we try to find a more cheaper outcome. So our goal was to keep our production cost around $10 to $15. And most of the upfront cost came from our microcontrollers. And I think Stefan, for example, mentioned that he had used an Arduino, which was also the main microcontroller we used on our end. And that actually contributed to most of the costs. So we try to keep overhead low to kind of maximize both cost effectiveness and signal fidelity. Now, there are trade-offs to this, and this is something I want to mention outright, which is being more budget conscious inevitably has certain trade-offs. So, for example, efficiency. But that's something we'll tackle, and I do want to present it later on. Now, here's a quote. I was reading during our research a project by the Harvard Law School Project on Disability, and it stated that poor people with disabilities are caught in a vicious cycle of poverty and disability, each being both a cause and a consequence of the other. So that sort of vicious cycle is something that we from Western countries are mainly immune from. And being able to kind of capture and target a way of solving that income disparity is something that's been my main focus throughout this. So our objectives, as I mentioned earlier, were a 10 to 15 cost or a budget on per product, and EOGs just simplify your just muscle movements. So it'll interface with any microcontroller. At least in our experience, we tested it with about 3 different Arduino types, and our signal to noise ratio, which is the difference between signal and noise, was around 37 to 39 decibels, which we believe is fairly high fidelity and can reduce a lot of disparities in the signal processing. We also wanted to make it open source in the sense that we want it to be easily accessible. So if someone were to, for example, commercialize this, it would be open to anyone who wants to kind of repeat that process, and that competition would drive costs down significantly. Now, our latency was also a main focus. Latency is the difference between the signal being processed and the actual movement. Now, this does not account for example, errors in human error, and it won't really impact the difference in signal that much. Now, the main thing I wanted to talk about was how the eye measured voltages. So that's a big thing that you can target via these low cost resources. So while it's easier and more, in a way, effective to measure eye movement with, for example, a sensor, having that electrode placed in your eye or around your eye can really capture, for example, an easier metric to detect with an external device. So the main challenge was in the microvolt range, so very little actual measurement, which is what usually happened when we had our baseline, which we found in research to be at a max about 1.2 millivolts. If you move down, that amount would fall significantly. So then once you're in that microvolt range, it's very difficult to measure anything. So that was our biggest challenge, but it's something I feel we addressed fairly well. And I'll show you guys some of the earlier outputs we had, and just to show the difference in measurements there. Now, another issue we had to target was that a lot of regulatory hurdles and issues with finding a sufficient pool of people willing to volunteer to have these measurements taken. We were only able to find 5. Now, this is mainly because this research paper was more of a proof of concept. We do want to expand this further, but it's mainly a way of showing that it is possible to make a cheap product that works, even though it's not the most efficient. It kind of trades that off for a cost, and it makes it more accessible to people from disadvantaged backgrounds. Like, for example, we communicated with I think 2 NGOs here in Brazil that have research experience or have volunteering experience with helping individuals from favelas. So favelas are also slums with poor income areas in Brazil, where there's very little access to resources. A lot of these people do not have access to, for example, schooling or proper healthcare. And it's something that's very difficult if you're, for example, the mom of someone with locked-in syndrome, and you're having to help your kid in this house on top of a hill, which is very difficult to bring down to a hospital. It's hard to find people that will go up there because of the dangers of actually getting there. So we wanted to kind of decentralize that a little bit by making it easier to build a device that could be easily accessible. Now, we had 20 different opportunities to measure these signals, and we try to recreate a more amateurish lab to see how good we could get our signal fidelity. Now, our system architecture is basically what we're following to kind of design this. The main thing I wanted to say with this was that it's a fairly device or component heavy system. So very little software dependence, and it's mainly just going to output certain signals. That makes it easier for individuals with these disabilities or these conditions to kind of access it. So someone's parents or a partner or a caregiver could easily access or be able to mess around and implement this for anyone. And the fact that it's fairly low, there's a fairly low footprint of it. We did apply for a patent to it, and I'm so sorry, but I forgot a picture of it. It's basically just electrodes being placed around the eye like this. So I think if you can see my camera, it's basically just placed one at the bottom, one at the top, and one horizontally. And then you have something here around your ear that would be used to detect discrepancies in the system when you move your eye up or down. So we wanted to make something very compact to kind of both create the sense that you're a more independent agent using it, because I know, as people have said prior, a lot of people with LIS are very happy, so they have a good quality of life. However, there's a trade-off, and I think this is something that I notice fairly often with family members who have certain conditions in which they're difficult. They need a caregiver. A lot of people do wish they had at least the semblance of a certain degree of autonomy or a high level of independence. And this kind of gives that impression by showing that you are the person controlling this, and that there's very little someone else has to do to make it possible for you to communicate. So that was our main topic, our main target. Here's the original results I wanted to mention. So these are some of the earlier readings we got. You can see that there is a kind of cascade near every upper limit here. And this is supposed to show the range of output movement from your eye. So looking down, you have a lower voltage. Looking up, you have a higher threshold. And then you see a sort of concentration of certain signals there that indicates that you're in the process of moving. So a lot of that noise probably came from the fact that we were using fairly outdated components. We wanted to kind of target things that were common in markets here. So for example, the microcontroller we used, or not the microcontroller, sorry, the components we used were, for example, from the 70s. So there is a large discrepancy in values, but it's what's easiest to access here compared to some of the higher tech components in other countries. Now, the results if I'm not mistaken, Shannon mentioned it earlier because I accidentally added the results of the research in the biography. But we had a signal to noise ratio that was fairly high if you were to account for only actual noise and not the movement process. And our latency was fairly low from the component itself and from a little bit of the signals from the device itself. You also have to account for reaction time, which is something that would shift that upwards. But from our very primitive kind of testing afterwards, we were able to find that this didn't really affect communication. Now, if I'm not mistaken, oh, there you go. So cost analysis. So this was the main thing I wanted to target, and I would be happy to kind of provide a brief description of this. So $10 to $15 was our range. Each of those amplifiers, which is something like the TL072, they cost 28 cents each. In local currency, that's around 1.2 reais, which is fairly cheap. That kind of reduces a lot of the cost. These electrodes were surprisingly the most expensive thing. So they cost $60 for a pack of 100. So it's costly if you buy it from a medical provider, which is what we did initially. So that kind of shows a bit of the bloat in the healthcare industry, and it's something we wanted to try to target. So if this were to be commercialized, advice to anyone thinking about it, maybe produce your own electrodes because they are fairly cheap and very expensive to buy. So that's just something to mention. So the advantages, as I mentioned prior, there were no optics. It was mainly based on electrodes and not cameras. However, oh, my coffee's done. It's my third cup today. So the main issue is that we kind of avoided using cameras because the software was too complex and we had a very small window of time to kind of optimize this. Our sources of error, as I mentioned prior, was because of the cost of the device itself. Sorry, the age of the device. So 70s components from the 70s are extremely outdated. Frankly, if you were to buy newer components, for example, some of the more efficient ones from this century still, you'd probably get it for, I think, twice that, which doesn't really contribute to cost, but it's something to be aware of. Electrode drift is a big thing, especially if you sweat easily. Having that basically salty water near the electrode can really impact the ability to capture signals. But that's something you could try to target by using calibration software. As I mentioned, software was something to try to avoid, but I think it could really be helpful. Now, cheaper components in age kind of reduce efficiency. As I mentioned, this could be remedied by more developed circuit design. If anyone has questions about the specific circuit design, I'm not sure if many people would be interested in knowing the exact circuit. I recommend you get in contact with Kieran. He did a lot of the electrical engineering behind certain aspects of that circuit. So if you have any questions, I'd be happy to forward your emails to him. Future works and adjustments. I believe Stefan, his product was something very interesting, which was a way of initiating conversation. If one could incorporate that into this device, I feel like it could be very helpful. So that's one thing just from this presentation that I believe is very, very interesting, as well as James and Tina's explanations, which I also believe could kind of connect everything and build something more efficient. Just brainstorming now. A big thing nowadays that you'll hear is using AI. Get overused in my opinion, but it's something you could really use to help understand patterns in movement. So there are a myriad of optimization processes here you could use. If any of you want this, I'd be happy to share the presentation, any sources I've used. And yeah. Now, it was mainly a proof of concept, as I mentioned prior. We are further developing this a little bit more. And mainly in the sense that we want to kind of reduce that noise and kind of optimize for the mathematical components of how we calculated certain latency and SNR variables. Now, I am sorry if this was very technical. My main point was mainly to talk about how there is a big gap between people and individuals from lower income backgrounds who cannot access certain technologies, and those who can. And a lot of the quality of life metrics, if you were to look into it, I believe poverty is something that could really contribute to kind of shifting it downward slightly, or the lack of independence, or any of the myriad of arguments we hear today, which are all very interesting. And I'm very happy I was here since the start because there are a lot of good things being discussed today. Now, as I mentioned prior, a lot of these are just repeated concepts I mentioned. And I want to kind of end by talking about how I kind of was motivated to pursue this. And a year or two ago, I was living in the Middle East for a while, finishing high school. And one of the stories I had heard of was from a Ukrainian family, if I'm not mistaken, who had fled to Canada, or not fled, had lived in Canada for a while, and their kid had locked-in or has locked-in syndrome, sorry. And the story of how they'd been able to access all of these remedies to help a lot of the conditions to kind of promote their quality of life and contribute to making a better outcome for their kid, and being able to kind of take advantage of things like neuroplasticity to recover some neural connections that were lost, or being able to communicate finally in one way or the other was something I thought was very interesting and what motivated me initially. And then thinking of this in the way that you're targeting people who were affected by poverty. Imagine if they had stayed in Ukraine or Russia or any of these Eastern European countries who now are so afflicted by war and conflict. Imagine how little they would have been able to actually help improve that quality of life. So something I want to leave in your guys' minds, and it's something I believe is a motivating factor for a lot of people, and something I believe is very something we must be aware of, which is the underlying afflictions of people who are already afflicted by conditions that can be very debilitating and limiting. So I want to thank you all for listening to the presentation. If there were any errors or mistakes, please contact me. I'd be happy to kind of understand a bit more of this. And if there are any questions, feel free to email me or Kieran, and just CC me, and I'll give them a heads up ahead of time. So thank you so much. And if there are any questions, I'll probably go to the chat now if there is anything. But thank you again.
That was really interesting. Thank you very much, Andre.